All right, so here's the problem I promised you guys. It's asking us to use the definition of a definite integral to evaluate the following definite integrals, and we are to use a right Riemann sum, and they're going to ask us for the right Riemann sum because that's going to be the easiest formula to use, and theorem 5.4, which is the summation formulas. So the first thing to understand is that the definition of the definite integral is this limit. And like it's kind of the same idea as the definition of a derivative was that limit, and then we found techniques to deal with it. You know, same idea. The definition is this limit statement over here, and you should feel pretty comfortable like looking at what's the same in each of these. And then we're going to manipulate it. So we are going to take a limit eventually, but the first thing is to find out what our change of x sub k is, and then what value we're plugging in. Now everything is exactly the same as it was before. So remember that our interval on this problem is 1 to 5. So that's our a is 1, b is 5. And so the first thing that we're going to do is find the change in x. And we're going to do that by subtracting 5 minus 1. And then we're dividing it by the number of subintervals. And if you look over here at our definition, the number of subintervals is actually just n. So then we're going to divide that by n to get 4 over n. The other value that we have to find is this x sub k, or x star sub k, or however you say that. And remember, they're asking for the right Riemann sum. So then we have this statement. This is from page 357. Okay, and so then we know the value of a. In this case, it's going to be 1. And then our change in x, we just found it as 4 over n. And this k is, the right Riemann sum is the k. So then when we evaluate this out, it's going to be 1 plus 4k over n. So now I'm just going to fill this stuff in to our limit. And then we can simplify this a little bit further because, just like any other function, whatever we are plugging into the parentheses is what we're plugging into x up here. So then I can simplify that down. So hopefully I don't run out of room here, but our function now is going to be 1 minus what we just found here. I'm totally going to run out of room. And then times 4 over n. Boom, look at that. 4 over. All right, so then to simplify that just a little bit further, we're going to have this statement still in a limit. And we have negative 4k over n times 4 over n. And so then finally, our most simplified version here is going to look like this. So now, they are telling us that we have to use theorem 5.4 here. So we are going to manipulate this a little bit. And so the weird thing is that we have two kind of different variables going on here. but really we're talking about K, right? K is our number of subintervals, or the number that, let's see, how do you say it? The subinterval that we're on. And so that's the one that we're going to be able to use. So the rest of this we're going to kind of treat like it's a coefficient. We're going to take that out on the outside here. So then we have still the limit as the change approaches 0. And now it's going to be negative 16 over n squared times the summation. And now we're going to use the theorem 5.4 on page 357 to evaluate the summation of k in terms of n. So now we have, let's see, let me get rid of this limit. Well, so I'm gonna ignore the limit just for a second, because we also have to do something with the limit here. So just this part. So here, let me do this off to the side. I don't want to say equals here. So just this part right, we know from those theorems is n times n plus 1 over 2. So we are still taking a limit now, and so I'm going to substitute this part right in here. Okay, and everything's going to be the same except for now we don't have this change anymore. And this kind of goes back to what we've been talking about, that if you're shrinking up the change in x to 0, then really what you're saying is that n's going to go to infinity. And so I'm going to change the, I guess, parameters of the limit to reflect that. Oops. So really now we're doing the limit as n approaches infinity. And now I'm going to re-bring in, right, we have this negative 16 over n squared. And then I'm going to simplify this new fraction here as n squared plus n. Oh, well, maybe I don't have to do that. Let me back that up. There's no need to do that. Right, so we're going to leave that alone right now, because we'll be able to simplify it a little bit. All right, so then simplifying that looks like, right, now we have negative 8 times n plus 1 over n. All right, so now we have negative 8n minus 8 over n. And now, if we directly evaluate that, and I can, just take the negative 1 out front. If we try to direct substitution of that, right, we would get this situation infinity over infinity. And so that's a perfect example of when to use L'Hopital's rule. So then, right, so L'Hopital's rule, and then we're going to get negative 1 times the limit as n approaches infinity of 8 over 1, which is really negative 1 times 8 equals negative 8. All right, and so then, if you think about like what we're saying here is that this is an exact value now, that we actually know that the area under this curve that we've been dealing with is negative 8. So like just, let's look at what that looks like as a graph here. So our original function was, where'd it go? Our original function was 1 minus x. Okay, so if we graph this, and we're looking at the interval from 1 to 5, right, if we graphed it, we'd start at 1, and down 1 over 1. Right, and so then we're starting here after starting at 1, and so it is going to be true that all of our area is going to be negative. And then, this is a nice check because we can just say like, oh, look, this is just a triangle, which was 1/2 base times height, which is 1/2, right? Our base is going to be 1, 2, 3, 4. And our height is going to be 1, 2, 3, 4, right? So then 4, oops. So that's an area of 8, and since it's below the x-axis, that's why we have a -8 here. So this was an exact estimate of the area. So I think, it gets a little weird. Oops. Because we're dealing with n a lot in this problem. But, I think if you work through this, once you get a hang of what's going on, I don't think it's too bad.